Thank you for attending our talk. Today I'll be presenting our work titled World-in-the-Loop Simulation for Autonomous System Validation. And I'm giving this talk on behalf of myself as well as Sebastian Elbaum. So let's begin. Imagine the goal of a quadrotor is to navigate through the gate using an onboard camera. The drone succeeds if it navigates through the gate, and it fails if it aborts the mission or if it collides with the gate. Let's look at an example of the same quadrotor attempting this in both simulation and in reality. In both, the gate is the same color and size. We can see that in simulation, the quadrotor succeeds, while in reality, it fails. Why does this happen? This difference in behaviors is caused by what is known as the simulation reality gap. The simulation reality gap describes the difference in sensor readings, actions, and behaviors between systems run in simulation compared to systems run in the real world. Developers can try to reduce this gap. For example, one might start development in a low-fidelity simulator, which has a very large simulation reality gap. Next, we might use software-in-the-loop simulation, which uses a simulated environment and simulated hardware, but uses the actual autonomous system software. We could further reduce the simulation reality gap using hardware-in-the-loop simulation, which uses a simulated environment, however it uses the real autonomous system hardware and software. These solutions reduce the simulation reality gap by bringing more of the autonomous system out of simulation, but still require the actual environment to be simulated, resulting in the simulation reality gap. The goal of this paper is to introduce a technique that allows us to close this gap. We call this world-in-the-loop simulation. This approach takes parts of simulation, as well as parts of reality, and combines them. And then depending on how we combine them, we can move between simulation and reality. As an example, we show a quadrotor taking off using world-in-the-loop simulation, where the camera data contains both parts of simulation as well as parts of the real world. In this example, we can see that the simulated gate is being placed in the real world, allowing the drone to experience an environment with real sensor data as well as simulated obstacles. So why is it difficult to take parts of the simulation and reality and merge them as suggested by a technique? Well, there are two main challenges. First, the autonomous system's operation, including their sensing and actuation, need to be synchronized in order for the sensor's values to be consistently integrated during execution. Second, a diversity of sensors, for example, cameras, lidars, microphones, and many more exist, each with potentially different data types, different data rates, and different formats, and each of them must be supported for integration. So let's take a look at how we designed our system and how we overcame these challenges. Here you can see our approach, which is broken up into three major components. First, we have parallel execution, where we execute multiple instances of the autonomous system in parallel with at least one in simulation and one in the real world. Then we have a pipeline for the collection and distribution of sensor data that allows us to read and pipe the sensor data from both systems into our integration mechanisms. And then finally, we have the integration mechanisms that combine the data from the different pipelines and feed it back into the original system. So let's take a look at each of these in more detail. So the first step is parallel execution, where we run both the simulation and real autonomous systems in parallel. This allows us to collect the sensor data from each autonomous system, where both systems are being run at the same time, and the data from the feedback loop is being used to keep both systems synchronized. So for example, we could feed the precise precision of the drone in the real world and use that, we could feed it back into the simulation and update the drone's position in the simulation to keep them matched and synchronized. By running these systems in parallel and creating the feedback mechanisms, we overcome the first challenge of sensor synchronization. The next step is the pipeline for sensor data collection and distribution. These are configurable pipelines built onto ROS, which uses a publish-subscribe architecture. This publish-subscribe architecture allows nodes to publish data or subscribe to it, allowing our technique to be fully configurable. The final part of our approach is an integration mechanism. The goal of this part of the technique is to create new sensor data that contains elements from both the real world and simulation. Here we use camera data to explain our approach, but it also applies to other sensors, for example, LiDAR and sound arrays. The integration has three stages. The first is to transform the data so that it is comparable, for example, by matching the resolutions. The second stage removes unwanted data, so for example, we could use color isolation to isolate the gate in the simulated data. Finally, we merge the data. In our example, we are using priority replacement with priority given to the simulated data. These three stages are designed to be general and thus allow for a wide range of sensors to be integrated, overcoming the second challenge of our approach, which was the need for a diverse range of sensors. The implementation of our approach can be found in the link on the bottom of the slide. Our implementation makes use of recipe files, which allows us to define both the pipeline and integration components. We start by defining different sensors under the AS sensor tag. In this example, you can see two sensors, both two cameras and a LiDAR. Next, we define the integration components in the combine tag, and the combine tag is broken up into transform, filter, and merge functions, which are described in the respective files. Currently, there are some limitations to our approach. First, the simulators that we use are required to allow for both read and write access of the sensor readings. And second, our implementation only focuses on camera data. However, this focus on camera data is not a limitation of our approach, which is designed to be general. The reason we only implemented our approach in camera data was due to the fact that the drone only had a camera. Once we had the implementation complete, we ran a study to determine if world-in-the-loop simulation does indeed reduce the simulation reality gap. Additionally, we wanted to determine if world-in-the-loop simulation can uncover implications introduced by the simulation reality gap, such as failures before any real-world deployments. For our study, we created three scenarios. The first scenario had a drone navigate through gates of different sizes. Specifically, we were interested in two sizes, a large gate that had a 1 meter diameter and a small gate that was 0.5 meter in diameter. This smaller gate was chosen as it was significantly more difficult to complete with only 10 centimeters between the drone and the gate when the drone was exactly in its center. If the drone passed this test, if it successfully navigated through the gate, and it failed if it crashed into the gate or aborted the mission. The second scenario had a drone following a person. In this case, the drone needed to stay inside a set area while following the person. The area was defined by a bounding box that allowed for at most an overshoot of 1 meter horizontally, while always maintaining a distance of between 2.25 and 4.25 meters away from the human. For this scenario, we varied the person between walking and running. The final scenario was obstacle avoidance, where one drone was tasked with avoiding another. The drones were placed 2.5 meters apart, and we had the second drone fly towards the first drone at both 1 meter per second as well as 0.5 meter per second. And this indirectly varied the time the first drone had to detect the incoming drone, determine if it was going to collide, and then avoid it. So here you can see the camera data from each of the scenarios in simulation and reality. The top row is gate navigation, the second row is the person following, and the final row is drone avoidance. And then by combining parts from each of them, we could create a mixed reality using world-in-the-loop simulation. Here you can see the results from world-in-the-loop simulation, which contains both parts of simulation as well as parts of reality. So, for example, in the gate navigation, you can see the real world, but you can also see a simulated gate. In the person following, you have gain of the real world. However, instead of a real human, you have a simulated one. And then finally, right at the bottom, you have the drone avoidance, where you can see a simulated drone instead of a real one. So for our study, we ran each scenario in simulation, and here you can see that there are 6 different test cases with gate navigation through a large and a small gate. We have person following with a person either walking or running, and we also have drone avoidance with the incoming drone either moving slowly or fast. So first we ran each of the test cases in simulation 5 times each, where all passed. And here we represent the data as a pie chart, where green represents a pass and red represents a failure. So in this case, you can see that there is no red as none of the tests failed. Then we ran each of the tests using world-in-the-loop simulation. And here you'll see that the results do not match the results we got in simulation. The data generated by world-in-the-loop indicates that only 2 out of the 6 were able to pass these tests reliably. And to confirm that these results were more closely aligned with reality, we ran the tests in the real world. So first, we found that in reality, the system can pass through the large gate successfully. Next, we showed that when you consider the small gate, the first test passed and the next test failed. and this crash resulted in a broken gate as well as the drone propeller being damaged, so the experimentation was stopped. We found similar results for the person following, that in both cases, world in the loop detected failures, and these failures were present in the real world even though they were not detected by pure simulation. And then finally, we found that the drone could successfully avoid an incoming drone moving slowly in the real world. However, due to the cost of failure, which in this case would be 2 destroyed drones, we decided not to run the final experimentation in the real world. And overall, we can see that according to our results, we have reduced the simulation reality gap, as the tests using world in the loop simulation more closely match reality compared to then just using pure simulation. So another benefit of our approach is that we reduce the cost of failures that occur in reality. So for example, consider a drone navigating through a gate using world in the loop simulation. Here, the drone operating using world in the loop simulation crashes into the gate. However, it has a much lower cost of failure as the gate was just simulated. This is compared to running tests in reality where there is a high cost of failure. So for example, in this case, where we did the same thing, however, when it failed, we had a broken gate as well as damaged the drone's propellers. So talking about future work, there are many directions we could take this work specifically. So for example, we would like to implement more sensor types such as LiDAR and sonar to confirm that our technique works using a diverse set of sensors. Secondly, we would like to incorporate more simulators. So for example, CAL and AirSim, both which are high fidelity simulators and they apply to different applications. And another line of interesting work is simulating more of the world. So what do we mean by this? Well, right now we can't introduce forces into the autonomous system in the real world. So for example, if we were to simulate wind blowing on the drone, it wouldn't actually experience these forces in the real world. And similarly, if we had a drone that was delivering parcels, is there a way to change the weight of the drone when it drops a parcel off? So these examples raise the question as to whether there are ways to introduce simulated forces onto the drone. With that, I would like to thank you for attending the talk. If there are any questions, please feel free to ask. And if I don't get around to answering your questions now, or you think of a question later on, please feel free to email me at the following email address. Thank you.